Hi, welcome back to my channel. And for today's video, we're gonna talk about silver aglaonema. I'm kidding. We're gonna talk about the kernel and range of linear transformation. So for those who have been here for a very long time, thank you so much for your undying support. And for those who are new to my channel, please don't forget to subscribe so that you'll be updated on a lot of videos that I'll be uploading soon, including these plans. So before I'm gonna start with today's video, I would like to shout a thanks to Jim Labahan for being so supportive with me with the channel and for endorsing the channel to his friends. To Jemima and Maria Catherine for being so supportive with me, and to Jovel. And of course, I'd like to give thanks to Carlo and to Rodolfo Maza for being so supportive and giving me the idea about the channel videos. And to Archie Vijar for giving me the idea to on what to do with the video. Thank you so much for all of these. Thank you so much. Okay, so let's start now. Okay, so suppose we're given with two functions here, the f and g here. And then your f and g are actually a mapping from v to w. And you consider elements here for every v1 and v2 in your v here. So that means it's coming from your domain. And if you're interested to get the sum of f and g here, whether it's a linear transformation or not, so we would have f plus g of f v1 plus v2. Remember that by the definition of a function, I can separate this like this. So this is by the definition of a function. And since f here is a linear transformation, so by the way, assumption here is this is a linear transformation, the f and g. And we're interested whether the sum is also a linear transformation. So I would have this f1 v1 plus f of v2 plus g of v1 plus g of v2. Now I can separate, I can regroup this one here like this one, and I would get f plus g of v1 here, and also this one and this one I can get f plus g of v2 here. So this means to say that the condition 1 of being a linear transformation is satisfied. Now let's consider a scalar. So we will say a scalar r coming from f, so the field here, and at which the vector space v and w is a vector space over this specific field. So let's say your v here is your vector from v. So taking f plus g of rv, that's simply f of rv plus g of rv. So that's actually this is actually r f of b, since f here is a linear transformation, and this is r g of b because g here is a linear transformation. So since r is a scalar, I can extract r from there, and I would get f of v plus g of v. And so I would get finally as f plus g of v. So condition 2 of being a linear transformation here is satisfied, which the moral of this discussion is that the sum of two linear transformations is actually a linear transformation. That's it. Okay, so now let's say we're interested. Okay, now let's say we're interested in being alpha and a given function f here. So your f here is a linear transformation and alpha is any scalar. So we will double check that alpha of f of v1 plus v2 here. So meaning to say your v1 and v2 here are coming from v. Your f here maps from v to w. So v and w here are vector spaces. So I'd get alpha of f of v1 plus alpha times f of v2. Observe that I can take the alpha here and I would have f of v1. And can take the other alpha here and I would get f of v2 here. This is actually by a common definition of a function, like a usual definition. So I'm gonna simplify and factor out alpha. So I'd get f of v1 plus f of v2 here. And so, actually, I'm done here already. So there's no need for me to simplify further. And so the condition 1 is being satisfied. Okay, that's it. Now, how about if we are interested? Let's say let's consider another alpha here. So you have alpha of f. So instead of using alpha, I use RV. That's it. So we'll see. Okay, so we'll see if the second condition is being satisfied here. So I would get alpha of f of RV. And then remember that I can extract f here is a linear transformation. So I would have r of f of v. And so these two things here are actually real numbers. So the commutativity of being a real number holds here. So I would have r alpha f of v. So therefore, the condition 2 is satisfied. And so another moral. Okay, so therefore, the condition 2 is satisfied here. And so another moral of this discussion here is that aside from the fact that sum of two functions, two linear transformations is linear transformation, the alpha f at which f is a linear transformation is also a linear transformation. That's it. Okay, so how about if we have additional linear transformation here? Let's say I would have H maps from W to U. So aside from having G as U to V, I'm sorry, V to W rather. So we have H maps from W to U. So how can we know if the composition of two linear transformation is linear transformation? So we will check again here. So these two vectors here are coming from a vector space V. And so by the definition of the composition, I would get H of G of V1 plus V2. And since G here is a linear transformation, I'd get G of V1 plus G of V2. And H here is also another linear transformation, so I can have this one here. Which simply gives us this H of G of V1 plus H of G. So condition 1 is satisfied here. Now let's double check the other. If let's say H of G of RV. So your R here is a scalar and your V is a vector. Okay. So this will simply gives us the idea that this is equal to H of G of RV. And since G here is a linear transformation, I would have this one here. And also H here is a linear transformation, so I can extract R from it. So I have R of H of G of V. And so I have R of H of G of V. So meaning to say condition 2 here is satisfied. And another moral would say that the composition of two linear transformation is a linear transformation. That's it. Okay, so we have now introduced that the sum of two linear transformation, the scalar product of a linear transformation, and the composition of two linear transformations are indeed a linear transformation. Let us recall first the basic of the functions theory. So here, we have a definition. So let V and W here be non-empty sets, and you have a function f from V to W. Okay. Okay. Number one, let U be a subset of V. Okay. So the image of U under F is the set f of u equals f of u, where your u here is coming from your u. So see the difference. This is a big U here and this is a small u. So your small u is coming from your big U. And remember, your big U is a subset of your V. So what does it imply? Meaning to say that the image of U under a function f is the set of all elements in W that are images of the elements of U. That's it. Okay, number 2. Let Z be a subset of W. So the preimage of Z under F is the set F inverse of Z equals the set containing V, which is coming from your big V, such that F of Z here is in Z. So the second definition implies that the image of Z under the function F is the set of all elements that is coming from V, okay, that are mapped to elements on Z. So that is the implication of the second definition. So this is actually in general the definition of a function. So if we talk about the map, which is a linear transformation, the image and the pre-image of a subspace are not just mere subsets of the domain and the codomain. In fact, these are actually vector spaces themselves, okay? Okay, so let me revise the definition of a function to be applied for the definition of a linear transformation. So in this case, you're given with, of course, these are actually non-empty vector space, the V and the W, and your F and B are not just it's not just a function, like, I mean, the mapping of F of to, F from B to W, is not just a function, but a linear transformation. So your U here is a subset of B. So instead of being a subset, this is actually a subspace. So the image of U here is actually a subspace of W. So in this case, this here is subspace of W. That's it. And also for second one, this F inverse of Z, this is also subspace of V. And that's it. So these claims here are pretty obvious, and I want you to prove this by your own. So if you have any questions or clarification, you can comment down there so that I would know and we can discuss that thoroughly. So I would just leave this by your own, but it's pretty obvious to show that this one here is a subspace of W, and this one here is also a subspace of V. Okay, that's it. Okay, so we will now introduce another definition here. So given that you have a mapping, so this mapping here from B to W here is actually a linear transformation. So the image, number one, the image of F or simply a range of F is actually the set here. So that's an image of F equals, which is the same as the set containing F of B, where your V is from B. Second here is the kernel of F is actually the same as ker F, which is the same as F inverse of the set containing the identity element coming from the codomain. So this is simply the set of V in the domain such that your F of B here is mapped to an identity element from the codomain. That's it. So how do we know that, let's start first with the kernel. So how do we know that the kernel of F here is a subspace of V? Okay, So to show subspace, so we have discussed that on how to show the subspace of a given vector space from the previous video I have made. So this time, we will show that here. If the kernel of F is actually a subspace of V. So let here alpha and beta be the element of the kernel of F. So if alpha and beta are elements of the kernel of F, it means to say that F of alpha and F of beta is mapped to a zero identity. I mean, the identity element of the domain, a codomain rather. Okay, so what does it imply? Um, your F of alpha plus F of beta, that's simply 0 plus 0. So technically, this is 0. F here is a linear transformation, meaning to say, I would have F of alpha plus beta. Okay, now this is 0, meaning to say that this one here is your alpha and beta here is actually element of the kernel of F. So, the first condition is being satisfied for the subspace test. Now, let R here be an element of the field F. So let us double check. R and F of alpha. So technically this is R times 0 because your F of alpha, I mean your alpha is coming from the kernel of F. And so F of alpha is 0. So this is 0. But this is a linear transformation, so I can equate this into F of R alpha. Meaning to say that F of R alpha is implying that R times alpha is actually an element of the kernel of F. So we have now satisfied the conditions for the subspace test. Therefore, this kernel of F is a subspace of the vector space B. That's it. Okay, let us see if we can show. Okay, all right. So let us say if we can show that the image of F is a subspace of W here. Okay. Now we have T of alpha and T of beta here are elements of the image of F. Of course, your alpha and beta here are coming from B. So, I'm sorry, why I'm using T? I'm using F here rather. So, meaning to say that F of alpha plus F of beta, because F here is a linear transformation, so I have F of alpha plus beta, which simply imply that because if you notice, alpha and beta here are elements of the vector space V. Now, V is a vector space, meaning to say that the sum is closed. So, therefore, alpha and beta are elements of V. I mean, the sum here is an element of V, implying that this is also elements of the image of F. Similarly, if you have a scalar here, elements of R, F rather, your field F, so you would get R F of alpha. Okay, this is a linear transformation, so I would get F of R alpha. I'm sorry, it should be B here. My bad. Okay, your V is a vector space. V is a vector for a vector space B, and so R times V is actually an element of V, which implies that this is an element of the image of F. Therefore, the image of F is a subspace of the W. Okay, so we will now introduce another concept here. So let's say we have, we have a definition here. So let's say our function f from B to W here is also a linear transformation. So the first is the rank of f. So we have a concept here for the rank of f denoted by this is actually the dimension. So this is the dimension of the image of f. So in other words, the rank of f is simply the number or the cardinality of the bases of the image of f. Number 2, the nullity, so aside from the rank here, we have the nullity of F, and we denote that by this one, like just in rt v. So this is actually the dimension of the kernel of F. In other words, this is the cardinality of the basis for the kernel of F. Okay. So before we proceed, I would like to make clarity on this. When we say the rank of F, so your F here is a linear transformation from V to W, we simply tell that this is actually the cardinality of the basis for the image of F. When we say the nullity of F, so we're actually getting the cardinality of the when we say the nullity of F, we're actually getting the cardinality of the basis for the kernel of F. That's it. So let's consider this one. Let's have a function f from v to w here, defined by sending the vector v to an identity element of the vector space w. So this is actually the previous example we've taken on the previous video, but we will continue that by identifying the kernel and the image. In that way, we can identify what would be the rank and the nullity of this given linear transformation. Okay, so if you would notice the kernel of f here and the image of f, okay, so this is actually all a mapping. Now, what's the definition again of the kernel of f? You're actually getting all the elements from your v, which are mapped to the identity elements of your w. Now, if you take a look into your mapping here for a linear transformation, all of the elements of your V here are actually mapped to identity elements of your W already, meaning to say that the kernel of F is entirely the V. And the image of F is actually the identity of your codomain. And so therefore, the nullity of F is actually the same as the dimension of V, simply because the kernel of F is actually the V. So whatever would be the dimension of V, and that will be the nullity of F. Now, if you are interested about the rank of F, so this is the rank of F here. Remember that all of the elements from your V are actually mapped already to the identity element, implying that your image of F is the zero vector. So meaning to say that this is 0. That's it. Okay, so let's have another example. We have a linear transformation from V to W, defined by sending V to V. So that means a vector V to a V. So we've shown this already on the previous videos that we have, that this mapping here is a linear transformation. So what would be the kernel of F? And what would be the image of F? Now, if you take a look into this, all the elements of this F are actually maps to the same element. So technically, the only way you can have a maps to a zero vector is when you have a zero vector from your domain. So therefore, the kernel of F here is just the zero of the vector space V. And then the image of F here, in this case, is actually the entire W. I'm sorry, entire V rather. Which implies that the nullity of F here is 0. And the rank of F here is the dimension of D. Okay, so another example, let Fm maps from R to R, defined by sending X to Mx. Okay. It has two cases, by the way. So, suppose if M here is 0, what happened is the kernel of Fm, this is entirely the R. Why? Because if M is 0, this here becomes 0. So, meaning to say that all elements from your R are actually mapped to a 0 value. So, the kernel of F is entirely the set of real numbers. Okay? And the image of F, in this case, is the 0. Why? All such elements from the codomain are actually the 0. So in this case, this is 0, 0, element of R. So in this case, the nullity of F, so what happens when F is not 0? I mean, when M is not 0, rather. So when M is not 0, so the kernel of Fm, so if this is not 0, then there's no way that this will be 0. Meaning to say that the only way we can map an element from the domain to a codomain to be 0 is when this is also 0. So therefore, this is 0. And so the image of F is actually of the form mx. Of course, technically, your x here is in R. Your x should not be 0. And remember, the set M, so I'm gonna erase this one here because I'm gonna generalize that. So the set containing M here, so a single set, is already the basis for the image of Fm. Simply because this is already like a linear combination. So, what does it imply? The nullity of Fm here. So what's the nullity of Fm? There are two cases. It could be 0 if M here is not 0, and this is 1 if M here is 0. Okay, the rank, however, of your Fm is actually 1 if M here is not 0 and 0 if M here is 0. That's it. Okay, so let's consider also another example we have taken from the last video. This is the mapping of, the map D maps from R sub n of t square bracket t to R sub n square bracket t. And this is actually this map defined by sending a polynomial phi of t to its derivative. Okay, so if you take a look into this, the only way we can send a vector coming from the domain to get a map of a 0 vector from your codomain is when you have a 0 as the derivative of that polynomial. And the only way we can have a 0 value for a given derivative is when that polynomial is a constant polynomial. So in this case, the only way to have our kernel of f is when it is equal to R. That's it. If you have any questions or clarification, you can comment down there so that I can discuss thoroughly. But again, the kernel of f here is the set R. And so the image of f, because this is actually the set of derivatives of the polynomial from your domain, so this is actually R sub n minus 1 of t. Why it's R sub n minus 1 of t? Because if you might want to consider a polynomial, let's say 3x, 3x squared plus 2, the derivative for that is 4x, it's 6x rather. So if you notice, the exponent is subtracted by 1. So in this case, this is now Rn minus 1 of t. So that is now the image of f, which implies that our nullity of f here is 1 because the basis of R is 1. That is a set containing 1, and that's the cardinality is 1. And the rank of f is actually n. Okay, so last example here is we have a mapping from R2 to R2. Okay, and we define such mapping by sending an ordered pair AB to a pair A0. Okay, now how do we get the kernel of F and the image of F? So if you might take a look into this, the kernel of F is when we map such elements from your domain to a zero vector. The only way we can have a zero is when A here is zero. Why? Simply because if you notice, whatever you put on your A, your B will always be zero in this case as the output of the map. In this case, the kernel of F here is the set of 0 B. B is in R. Okay, so whether B is 0 or not, it will still end up being 0 by this definition of the map. Okay, and the image of F is actually of the form A0. That means to say that whatever you do with the mapping, you always have the second ordinate of the output as 0. A here is in R, which implies that the nullity of F is 1 because the basis for this is actually 1. And then the rank of F here is also 1. Okay, so we will end this video by introducing a theorem that is actually a powerful theorem for you to understand such dimensions of basis for kernel and image of a given linear transformation. So we call this a rank-nullity theorem, which simply says that if you have a V and W be vector spaces, over the field F such that V is finite dimensional. So requirement here is B should be finite dimensional. And suppose your F here maps from B to W is a linear transformation. Okay, then simply we would get that the rank of F here plus the nullity of F is actually the dimension of B. So if you might notice on every examples that we have previously, if you take the sum of the nullity and the rank of a given linear transformation, that is actually the dimension of the vector space of the domain. That's it. So let's go back to the previous example. Okay, so let's go back to the previous example. The mapping F from V to W defined by sending V to every to the identity element. If you remember, the nullity of F here is the dimension of B, and the rank of F is 0. So if you take the sum, that is actually the dimension of B. So that's what it says about the theorem, the rank nullity theorem here. So I will give you the outline of this proof here by simply assuming that n here is the dimension of B, and k here be the nullity of F. So the kernel of F is always a subspace of B. So this implies that 0 is always less than or equal to k and is always less than n. So what happens when k is 0? So when k is 0 here, this simply tells us that the kernel of F here is the set containing 0 vector of V. Okay. Now, let this W1 up to Wn be basis for the image of F. So what does it mean? This simply tells us that there exists V1 up until VL in V such that you have a mapping of F of BI to WI for every I greater than or equal to 1 but less than or equal to L. So meaning to say some vectors of B are actually, how do I get that? Some vectors of V are actually mapped to WI. So this implies that the set containing V1 up until VL is already a basis for B. This implies the dimension of V is actually the rank of F. And so, it holds. Why? Because your kernel here is 0. Now, what happened when k is not 0? It's equal to 1. So when k is 1, this implies that f here is at 0 linear transformation. So that means this is the only linear transformation. And so this implies that the image of f is actually the set containing 0w. So we're that on this case. Now, how about if k is between 0 and n? Okay, so if k is between 0 and n, we let the bases u1 up until uk be a basis for kernel of f. This is also a linear independent set, linearly independent subset rather, of what? Of course, this is a linear independent subset of V because this is actually a basis for the kernel of F. So meaning to say that this can be extended to a basis. So in this case, we consider S here the set U1 up until UK, and that's UK plus 1 because we extend that up until UN. So our goal, by the way, the rank of F is equal to N minus K. So we will assume that we have another set S prime. In this case, this is the image. And we will show that this S prime spans image of F. So we will show that that spans image of F, because if that spans the image of F, and this is a linearly independent set of vectors, then this is also a basis for the image of F. Thus, W is equal to F of B for some B in V. Okay? So if that is equal to F of B, then there exist scalars A1 up until AN such that your V can be written as this. Remember that F here is a linear transformation, and so F of B, if I'm gonna take F of both sides, this F of B becomes W, and this is F of this thing here. So I'm gonna write this thing here, and that's actually equal to A1 of F of U1 up until AN F of UN. So this is just simply writing as F A sub K plus 1 of F of UK plus 1. Okay. Up until you get AN of F of UN. So meaning to say there we arbitrarily replace 1 by K plus 1. So the image of F can be written as a linear combination of the elements from S prime. So this implies S prime spans image of F. Okay, so we're done that S prime spans image of F. So we will show now that S prime is a linearly independent set of vectors. So let A1 up until AN minus K in F. So these are scalars such that I'm gonna write A1 F of U K plus 1 plus A2 F of U K plus 2 up until an minus k of f of un equals 0. So that's actually a 0 vector. In this case, we only need an minus k because there are only n minus k mappings here. So if this is equal to a 0 vector in W, which is a codomain, this simply tells us that this is an element of the kernel of F. So this, if you notice, this is equal to the 0 vector, which is an identity element of the vector space W. And so, and remember, F here is a linear transformation, so I can just have this equal to F of A1 UK plus 1. And then, along with this, and then you can combine because the identity of the first definition for linear transformation is that you can have this. Plus and so on. Okay? Which implies that A1 UK plus 1 plus A2 UK plus 2 up until AN minus K of UN. This sum here is actually element of the kernel of F. Thus, there exists B1 up until BK such that I would have A1 UK plus 1 until AN minus K UN. That's the same as B1 U1 up until BK UK. I would have B1 U1 plus until BK UK. This is minus A1 UK1 plus 1 minus up until minus AN minus K UN equals 0. So that means I transfer all these terms here to the right side and then equate that by 0. Okay? So just a basic algebra. This is 0 vector. Simply the 0 vector from the domain, simply because these are actually elements of the kernel. So since S here is a set of linearly independent vectors, this simply tells us that all AI here is 0 for every I, such that 1 here is less than or equal to I, less than or equal to n minus k. And this is also implies that Bj is 0 for all j, such that your j is between, greater than or equal to 1, but less than or equal to n minus k. I'm sorry, let me correct. No, it's k rather. Hence, your Si prime, your S prime rather is linearly independent set of vectors. And so S prime is linearly independent, and at the same time, it spans the image of F. And so S prime is the basis for F, and which implies that the image of F, the rank of F, is actually n minus k. That's it. So we have now proven the claim. Okay, so thank you so much, and that's all for now. Thank you so much for watching. So if you have any questions or clarification, you can comment down there so that I would know and we can discuss that thoroughly. So thank you so much, and again, don't forget to subscribe to my channel if you haven't subscribed yet. And for those who have been here, thank you so much for supporting me for a very long time. Thank you, and have a great day.